A geometric dissection is a set of pieces that can be assembled in different ways to form distinct shapes. For centuries, the counterintuitive properties of dissections have fascinated us. Classic examples include this 4-piece dissection between a square and a triangle, and the ancient Chinese 10-gram puzzle. Unfortunately, existing dissection puzzles are limited to simplified or geometrically ideal shapes. This limitation arises because dissections of more complex shapes usually require an extremely high number of pieces. In this work, we introduce a dissection design technique that largely sidesteps this problem. Our technique can produce dissections between complex natural shapes with a small number of pieces. Our technique is based on the observation that when creating a dissection between two natural shapes, it is sufficient for the dissection pieces to approximate rather than exactly reconstruct a shape. For geometrically well-defined shapes, such as this triangle, we immediately notice any distortions. However, for geometrically complex shapes that are method targets, such as this dog's head, distorting the shape slightly does not affect our overall perception of the object. To formalize this observation, we define the approximate dissection problem as follows. Given a pair of input shapes and an integer k, we seek to find a set of k pieces that can be assembled into shapes such that the shape difference measured between the original shapes and an assembled shapes is minimized. We have developed a technique for solving this problem which uses a search tree to locate dissections that closely approximate the input shapes. We introduce a way of representing dissection solutions that allow the definitions of a lower bound on the quality of a partial dissection solution. The lower bound allows us to prune branches of the search tree, making the search tractable. For further details, please refer to our paper. We also developed a graphical interface tailored for editing dissection designs. Here, we show the initial dissection design from our automatic approach, which has some problematic areas. We present suggested edits to the input shapes, shown here as red curves, which would make the dissection generation easier. We also allow the user to mark salient regions on the input shapes. Our method will adjust the dissection to preserve these regions. We now present some dissections created using our technique. Here we show a fabricated dog to bone dissection that can be used as a challenging puzzle. The pieces are capable of being assembled into false solutions, which substantially increases the difficulty. We have presented an approach for creating approximate dissections. This is the end of our video. Thank you for watching.